I'm back. So I can ask, can everyone hear me? Or can anyone hear me? Okay, very good. So let me share the screen again. Sorry about this. The first day. So okay. So screen again. So let me actually go back just so you have something to see. And again, ask, sorry. Can you see the screen? Although you might only be able to see half of it. Okay. So let me try not to sign out as I rotate. It's not rotating. There it goes. And again, so there it goes. So we have the solid cylinder, and so we want to find where we have a particular density. And in particular, let me just say it is something simple. As I said, if you do have questions, stop, and I'll come back to you. I can't, since I'm in a different screen, I can't easily go back and forth. So let me set up the picture, then I'll go and ask you and see if you have questions. So we're looking at a cylinder. And as usual, I can't draw it very well. And you can see, since the cylinder, I'm going to want to look at it in the XY plane. And so if I look at the projection, I get the circle in the XY plane. So this, I'll go back and ask a question, which is, what I want to know is what type of coordinate are we going to use? And let me start the integral. And ask you, since this is simple, what are the limits for z? So I'll leave it up here for a second to make sure you can see it. So two questions. First, what type of system are we going to use? Are we going to use either rectangular or cylindrical or spherical? And second, what are the limits for z? Oh. Yes, sorry about that. If I can actually. So there's the bottom half of the first page again. So let me leave it there for a minute. So it's just a really basic one. The solid cylinder, x squared plus y squared is less than or equal to 9. It's solid, and from z equals 0 to 2. And then the density is on the next page. So cylindrical is correct. And what in some ways, since I'm seeing a lot of people having it go back and forth, what I will do is at the end of this, this is being recorded, but I will also write it up a bit neater, scan it, and put it on Blackboard so you have a neater version of this. So you will get this where you can see everything at once. So as I said yesterday, this is going to be a mess. It's kind of the first day I've ever done this. And someone has said it's 0 to 2, which is correct. So I put that. And now what I want to know is, since it's cylindrical, Z will say it as is. I'm trying to write in a different way, so it's going to be a little messy. You're going to see what happens to the rest of the integral. So first, what does the rest of it become? Z times what? Oh, sorry. I heard the same question going back and forth. So Z times R cubed, someone says, because the x squared plus y squared becomes R squared. And then we get our usual R with the dr d theta. And what are the limits for the outer two integrals? And I think you can still it on your screen. I'm back to the main one. So 3 for R. So that's supposed to be a 0 to 2 in the inside integral. So 0 to 3, and then because it's the full circle, 0 to 2. So let me fill that in. It'll be messy because I'm trying to stay on the one screen. Okay, so I get that. So as I said, I'll write this up neat for put it on black. So the limits are 0 to 2 pi, 0 to 3, 0 to 2. And we leave Z as it is. And if we're actually going to do it, then of course we would make it 2 times R cubed. So as I said yesterday, it really isn't anything new. We're still doing cylindrical. But any questions on this one? And in some ways, just chat thing, as I said, I'll delay a bit to if you have a question because lagging, so sometimes not. So I see some people are typing, but so I'll wait a little bit. So actually, I'll say something as I'm waiting, which is so you can kind of guess what I'm going to do for the next example, which we did a two-dimensional one. Now we did a cylindrical one, so now we're going to do a spherical one. So do it as an example instead of doing one of the problems from spherical. And so one person asked just the one. So you should have the two-dimensional one from the previous example and three-dimensional one where I didn't. So interesting. So some people are saying it is frozen. So let me just check again. So I'm now going back to the main application. So here is the first page, which I'll leave here for 30 seconds. And then I will go back to the second page to see if, because some people said they didn't see the last thing I wrote. So, and now can anyone, this way, anyone not see this second integral, the 0 to 2 pi, 0 to 3, and 0 to 2? Interesting. Let me make sure it's still being shared. So let me try writing something different and see if you can see that.
the screen is so frozen because when you switch to the first page, it was still stuck on the second page, and if you're still only see the initial integral of the cylinder and the two diagrams.
Okay, so let me write this and see what happens. It could be that it wasn't seeing it because I was doing it inside of another application. So I have a new one, and so you're going to tell me if you see it or not. So it should be for the sphere something something something. Okay, so it could be that it doesn't like showing the second page. So what I'm going to do is I will do the internal whiteboard, which isn't as nice because it has a smaller screen. But let me go to that and again ask if you can see it. So here I'm sharing a blank whiteboard. So let me just stop there because I don't want to go too far if you can't see it. So this one, it sounds like you can see. Okay. So I'll stay with this one. This isn't as nice because it doesn't let you go to a second one. So what I have to do is erase the whole thing. And so kind of like a board. So we have the solid sphere, x squared plus y squared is less than or equal to whatever I said, 9, I think, in the first octant. And also, as you can see, it also starts writing if I raise it with my finger, so ignore stray marks. And again, do kind of one. This is a new problem. As I said, what I will do is, so you have everything nicer, I will write it up, scan it, and put it on. So we have a new one. We have the solid sphere where x squared plus y squared plus z squared is less than or equal to 9. I'm just going to look in the first octant just to make it not too simple. If the density is, again, simple, let's again find the mass. So see if I can draw. It's just the sphere, it's supposed to be a sphere in the first octant. And so again, the question, which type of coordinate system should I use? Pretty obviously, hopefully in this case. This will be spherical. And you can see it's a simple one. So we will do the triple integral of the z, which we'll have to write in spherical coordinates. So the two questions are, what is z in spherical? Which I'm just going to write, and you're going to, because it's going to be a pain to try to write things like rho sine of phi. So in this case, I'll put that in. So that's Z. And then similar to the two-dimensional one, since we're doing it with spherical, we have the extra piece in. And again, I'm not going to try to make right this. Let's put in that we always get this, which remember is rho times r, because r sine of phi. And let me ask you, what are the, and sorry about the frame, what are the limits? So for the inside one, for the rho, the limits are from where to where? Oh, and some people will give me more. So the inside limits are 0 to 3. The middle one, phi, goes from 0 to pi over 2, because remember it's going from both sides, although here only not really. It just happens. Whereas if we wanted the whole thing, that's supposed to be pi over 2. It would go from 0 to pi. So remember, for theta, all the way around is 0 to 2 pi. For phi, it's only from 0 to pi. And so someone told me the other one is also 0 to pi over 2. So I said I'll write this neater. So it's supposed to read limit 0 to pi over 2, 0 to pi over 2, 3, and then the rho cosine. So any questions on this? And this is, now the reason I didn't want to use this one is this pretty much all I can do is just erase. I can't go to a new page. Seems like I can't on the other one either, but so what I'm going to have to do is just erase and go to a new one. So before I do that, and to give you time, any questions on this one? Okay, so I will erase. For the weekend, you're going to try the example. So in some ways it's nothing new, but try the examples for this section 3.8. At this point, the next section in some sense 3.11, and I thought this quickly yesterday. What we want to do is we have a three-dimensional object, surface area of the object. But to do that, we need to look at the parameterization of the function, and we haven't officially done that. So let me go back, and we're going to look at 2.8. Which is looking at parameterizing functions. In some sense, you should have done this either in Calc 2 quickly, or you probably will have done this in physics. And the idea is just to take a regular function, introduce a new variable, which often is time, and rewrite the function as a vector function. So for example, here, a really easy thing to do would just be let x be t, and then y is equal to x, which is t squared. So the same function as a vector function, y equals x squared, is the vector function t comma t squared. And we introduce time, so now we can talk about moving along the curve, not just seeing the curve. And so this type of thing we can pretty much always do. So if I give you something more complicated, sorry, I can't erase, that's supposed to be a z squared. So, as I said, I'll make it neater. I could do something similar, except now I have 3 variables, so I'm going to have to introduce 2 new variables. So I could do, for example, x is equal to s, y is equal to t, and then z is equal to, since it's not a function, I will need 2 pieces. This. So pretty much, it's always easy to do a basic parameterization or vector function version by just letting all but one of the variables be a new variable. And it's I can easily just leave it as x equals x and y equals y. But this is showing I really am rewriting it as a vector function. And so now the new vector function here would be that. If you graph this, it would be the same graph. But as you might expect, this really isn't a very nice parameterization. So the easiest one to get isn't always the best one. So this one is not the best one. And from the previous example, you might guess, what do you think the parameterization for this thing will be? I think we'll let x, y, and z to make this a bit nicer, since it's a sphere. So since it's a sphere, we should use spherical coordinates. So therefore, it looks like I'd introduce one more variable, but of course, rho here is actually fixed. What is rho here? Yes. So again, we have two variables. So we've introduced variables. Again, we can move along the sphere, and instead of just saying here's the sphere. So we've introduced two variables to say, well, what happens if I move along S or I move along T? So again, I'm going to have to erase, so give you 30 seconds to. Oh, right. Someone knows. So I can't erase, but someone knows my usual mistake type things. That should be sine phi sine theta. Thank you. So any other comments before I erase and go to the next thing? Let me erase. So there are a couple of uses for this. First, in some ways, the most basic one is it allows us to look at more complicated curves. And this is not something I can easily do with the regular function notation. So if I look at this, if you think about what's going on, if you just ignore Z for a second, of course, going around a circle. But since Z is increasing as time goes along, what we're doing is we're going along a spiral. So this is, we're moving along a spiral on the outside of a cylinder. So it lets us describe more complicated curves, because if you think about it, this would be not even necessarily a function if I did it in regular function notation, because at different values we're getting the same thing, sort of. For us, we're really just going to use it to, at least first, to get surface area. So make it easier to talk about surface area, because we'll be moving, we can talk about moving along the surface. Before we do that, we will want to make sure the function to be nice. And so someone said, I'm going to wait a second because someone said there might be something wrong with my mic. So say something, just tell me, can you hear me? My Zoom off, so let's see where's my microphone. I'm not sure. So in case you do have trouble with this, and I'll have to check, see what's going on. Seems to be okay. My connection is okay. So let me say something again. Is it any better? Okay. Good. Connection might be going in and out, so maybe it's the connection that every once in a while goes out. So we want it to be nice, and so we're going to define a particular case. And since I want to put it all on one page, let me erase this and go to a new page so I can put everything on one. So we want it to be what's called regular, and something is regular parameterization if it has a few characteristics. First is make it so it's not disconnected. So the points we're going to plug into the function are nice. First, there are points, so it's not just nothing. Second, it's all connected, so there isn't a piece at one place and then nothing for a while and then another piece. And open just makes things nice so that we don't have to worry about boundaries. So what we're looking at, the base is nice. So we're looking at R3, but the idea is if you look back at the last example, when we did the sphere, we had two variables because we're getting a surface space in 3 dimensions, but it's a 2-dimensional surface. We're in 3 dimensions, but we're looking at 2-dimensional surfaces. So we want that to be nice, the numbers that we're plugging in, so we're getting something that isn't disconnected in 3 dimensions. Second, as usual, we want the function to be fairly nice in the sense that it has derivatives and is defined everywhere. Right, so someone says that the parameterization is in R3. So as I said, the two pieces are that the surface we're looking at is in R3, the set W is in R2. Because if you look at the last example, we got the sphere, and we parameterize it with only 2 variables, theta and phi, because rho was fixed. So W in that case is all the values of theta and phi that will give us that sphere, which in this case would be theta goes from 0 to 2 pi, and phi goes from 0 to pi. So that's nice space. So we want it to be nice in the sense that it is differentiable everywhere as usual, that the derivative works. And 3, we want the two partial derivatives to be linearly independent at all the points. And this has two ways we can do it. The first way, if you've seen linear algebra, you know, is the official thing is two vectors are linearly independent if the only way a times one vector plus b times the other vector is 0 is if the two vectors are 0. This definition generalizes to however many vectors we have. So if there are 5 vectors, again, linear combinations equals only if all the constants are 0. So here a, b, and are numbers. In 2 dimensions, this of course simplifies to one is not a constant multiple of the other. Oops. Is cross that out is not equal to. So one is a constant multiple of the other. So someone asked the first condition for 3. So we want the two partial derivative vectors to be linearly independent. Is that what you're asking? So let me say that something is regular if it has 3 things. First one is pretty much usually true for us, which is the values that we're plugging in, the 2 dimensions, because we're only going to look at surface area in 3 dimensions. The 2 variables are connected. So I don't do something like x goes from 0 to 1, and then x goes from 1 to 5, 2 to 5. It's connected, so it's nice. 2 says that when I look at the functions, individual functions, y and z, they're all fairly nice. So in the sense that they're defined at all the points we care about, and the derivative is defined at all the points we care about. And then the third one says that the 2 vectors are linearly independent in 2 dimensions, and one is a constant multiple of the other one. So that's pretty easy. Third one, there's going to be a second wave check, which we really wouldn't normally want to do, but it's going to come back when we use it, so it'll end up being something we're going to have to get anyway. And this is a linear algebra thing. So erase this. Let me ask again, any questions on what these mean? Okay, so erase. So another way of saying it, vectors are linearly independent, is if their cross product is non-zero. If they are linearly independent, then when you do the cross product, you'll get the 0 vector. So if you remember cross product, which we did near the beginning, that's a bit of a pain. So if all we care about is if they're linearly independent, we wouldn't do this because it's just more work. But we will eventually want the cross product, so we'll try that. So let me do one example where you could have a problem that is most regular but not quite. And that's supposed to be square root of x squared plus y squared. So that's top half of cone. So we want to first get the parameters in, and let's use the really basic one, so that's where there's going to be the most trouble. So if I do just basic, and I'll use my stray mark there. Then to see if it's regular, we first say that, well, we're plugging in any values of x and y, so that's fine. And now we need to look at the partial derivatives to see if they work. So in this case, we're using s and t instead of u and v. So the derivative of this vector with respect to s is the derivative of x, which is 1, derivative of y, which is 0, derivative of z, which is the 1/2. Write it. So it's going to be 1/2 times s squared plus y squared, s squared plus t squared to the negative 1/2 times, in this case, 2s. So the 2's will cancel, and I'll get this. So one of the two is pretty obvious. Are these two things linearly independent? So is there a constant? So if I multiply, say, rs by that constant, I get rt. Is that possible? No, pretty obviously not, right? So they're obviously linearly independent, but the other thing we need is that first the derivative works everywhere, the function is everywhere. That's okay, because since we have s squared plus t squared, we always get a positive value. So the square root always is defined. But where is there a problem in terms of the derivative? And I'll start writing it, not regular at. So where is this not defined, where the derivative is not defined? And it's in the obvious place, hopefully. The usual thing, we can't divide by 0, so and in some ways, there's a bit of a lag with the chat, so I should wait more for answers for questions, sorry. And if you think about it, this makes sense. So picture a cone. Then obviously there's going to be a problem at the point at the origin, because you have lines coming at it from all different directions, so the slope changes abruptly as you're moving around. There's going to be a problem at 0. So this one, the cone is regular, except at the point s and t equals to 0. And first, that's about the worst that we can get. So it is regular if we get rid of the origin. So same as usual is there are only problems at the usual types of things, which is when we're taking square roots of negative numbers, we're taking natural log of negative numbers, we're trying to divide by 0. So there'll be problems there, and it might not be regular. So what I want to do is from here, and I think I'm going to stop because I don't want to get too far in case I messed up a little bit, and give you a chance to write things up. So yeah, so someone asked, so what are the purposes of doing this? And that's going to be, we're going to get into on Monday, which is by rewriting it as a parameterization, we're going to be able to get the surface area. In regular coordinate system and as a regular function, it's going to be difficult to get the surface area. It'll be much easier if we're doing a parametric form. And so therefore, we want to talk about parametric form, and for work for the surface area, we need it to be nice. So we'll be able to use this to get the the surface area. And to get the surface area, we're going to need the cross product. So we might as well get the cross product to see if the vector is 0 or not. So for the weekend, so this is stop here a little bit early, but let me do a couple. As I said, look at the 3.8. This we haven't really finished, but if you want, you can start reading through this section, 2.8. Later today, I will put onto Blackboard the quiz you would have gotten today, but for now, it's just practice. You don't have to do it. You can ignore it. I will eventually put up answers, but if you want, and this will be practice with me checking, see if I can do this for an actual quiz, is you can try it as if it was a quiz, send me it, I'll grade it as if it was a quiz, send you back the you would have gotten, and then I'll put answers back up, the actual answers up on Monday. So that way you have a chance to try it on your own. I see if the system works where I give you a file, you try it, you send it back to me in some form, either by scanning it or taking a picture, which might be what we have to try for the test. It will not be next week because it'll take a little while to figure this out. The thing is, in terms of office hours, for now at least, they haven't told us not to have in-person office hours. I'll be here from 1 to 3, and as long as not too many people show up at the same time, it should be okay. But I will also have Blackboard open, so send me an email. If you can't make it, send me an email telling me that you want to do office hours on Blackboard or something like that. I'll sign in, set it up, and we can talk through Blackboard. So hopefully this wasn't too terrible. As I said, I'll write up the notes later and put them on Blackboard today. So have a good weekend. So Julie asked, we should study 2.8 and 3.8. So really backwards. 3.8, which is nothing new, it's just the mass. So just more examples of three-dimensional things to try. And we haven't really finished this section. So you can start, but don't worry about it too much yet. And then Monday, what we'll do is we'll do an example kind of all the way through 1 or 2 of these from this section and lead that into the next section where we're actually using it to get the surface area. So that'll be where we actually use it. So I'll stick around for a little while, but that's all new I'm going to do. So I'll stick around online here for a couple minutes. So if you have any quick questions. Otherwise, as I said, have a good weekend.